All right, so let's look at an actual example of scattering and see how this actually works. And again, first example we're going to look at is Rutherford scattering. So again, Rutherford's famous experiment where he shot gold atoms then at a target, or actually, sorry, he shot alpha particles at a piece of gold, and then basically noticed that he was getting recoil going backwards, which basically led him to discovery of the nucleus. So here we're going to consider, again, this repulsive potential, which is given by this positive sign, which basically means that what? Both the nucleus and the alpha particles had exactly the same sign to them. I think they're both positive, which caused that repulsive. If this wasn't attractive, we would just have a negative sign here. So Z times E then is going to be the charge of the nucleus, or of the target in this case, and then Z prime times E is going to be the charge of the particles that I'm going to use to scatter with, which means that the potential then is going to be the total charge, which is Z times Z prime times E squared divided by R. So from here, first thing we're going to do is, again, plug this back into our R0 to figure out what that guy actually is. So to remind you, that was R0 squared times 1 minus the potential divided by the energy, minus the impact parameter squared is then equal to 0. So plugging this guy in, I get an R0 squared minus then Z times Z prime times E squared divided by the energy. And then here I have an R0 squared divided by an R0, so that's just going to be R0 minus the B squared is then equal to 0. So again, this gives us a quadratic that we have to solve for R0. So if I do that, I get R0 then is going to be equal to 1/2 of ZZ prime E squared all over the energy plus the square root of ZZ prime E squared over the energy, quantity squared, plus 4 times the impact parameter squared. So notice here I'm keeping the positive sign. I'm keeping the positive sign because here I have a positive sign, which means the discriminant, again, is bigger than this first term, which basically means that since R0 has to be a positive quantity, I have to get rid of that negative sign, which means that, again, there's only going to be one R0, which is consistent with what we talked about with orbits. So again, if energy was too high, we wouldn't have 2 turning points. We'd only have the 1 turning point. So when a particle comes in and then escapes back outward. So good. So then we know where R0 is. So in this case, we can now determine what is the scattering angle. So let's determine our scattering angle. So good. So remember, our scattering angle theta is going to be the same thing then as pi plus twice the integral from infinity to R0 of then R times the square root of R squared, 1 minus the potential, which now is Z prime E squared, divided by R divided by the energy, minus the impact parameter squared, integral B dr. So here I've actually inserted what then V is and left it as a general function of R. Now one thing I'm going to do is I'm going to change the sign of this. I'm going to make this guy a negative sign so that way I can rotate the order of the bounds. So I'm going to integrate this from R0 to infinity. Good. Now next thing is I'm going to define a new parameter. So let's define our new parameter U, which is equal to 1 over R. So that in this case, du then is going to be equal to what? Minus dr over r squared. So meaning that dr then is going to be equal to what? So minus du times r squared, which is the same thing as minus du over u squared. So that's this guy. So plugging in here, and then basically reducing, what I get in this case then is this becomes equal to, so this negative then will make this guy a positive, so it's going to become pi plus 2 integral from u0 to 0, because in this case, actually this is 1 over u0. No, that's fine. So u0, and then 1 over infinity is the same thing as 0. So this is now going to become b du integral So this is now going to become the square root of 1 minus z prime e squared divided by e all times u minus b squared times u squared. Now, if you go back into notes, what you'll basically notice is that this integral that we did here is the same as what we did for the orbits, which means that we know the value of this integral. This is just going to be that inverse or arc cosine. So if I match all the correct parameters, what I get in this case then is that this is going to be the same thing as pi plus twice of the inverse cosine of 1 plus 4b squared b squared divided by z times z prime e squared squared square rooted 1 over. Good. So good. So like I said, basically what this is going to do is it's going to give us then theta as a function of b. So from here, all I then have to do is what? Basically solve this guy now for b. So if I do that, first thing to note is, let's go ahead and solve this guy now for b. Get rid of all this stuff. Don't think we need any of that. So good. So good. So from here, we're going to get a cosine squared of theta over 2 minus pi over 2. So basically all I'm doing is I'm dividing both sides by 2. So I'm subtracting that theta to the other side, and then dividing by 2, and now taking a cosine. And now I'm going to square that cosine, basically get rid of that square root term. So if I do that, then this is going to be the same thing then as sine squared of theta over 2. Which is then equal to cosecant squared of theta over 2, 1 over, which is the same thing as, again, getting rid of that square root term, 1 plus 4b squared e squared divided by z prime e squared 1 plus e squared, this guy. Okay. So that's the first thing. So again, now what I want to do is solve this guy for d. So finally, if I solve this for b, what I get in this case then is that b then is equal to z prime e squared divided by twice the energy times then cotangent of then theta divided by 2. So now I have this. So now if I want to find that differential cross-section, all I then have to do is consider the derivative of this guy with respect to theta. So if I do that, I get a minus z prime e squared divided by twice the energy. The derivative of cotangent is the same thing as cosecant squared of then theta divided by 2. But I also pick up an extra factor of 2 here, so this actually becomes a 4. Now, let's plug that in. Then our differential cross-section is going to be the same thing then as what, d divided by sine of theta, db d theta. So now we know db d theta is this. We also know b is equal to this, divided by sine of theta. So at the end of the day, this is going to become equal to z prime e squared divided by 2b. So I get this guy, so I got 2 factors of this, and I have a 4 here, and then I got a 1 over sine to the 4th theta over 2. So good. So this is then my differential cross-section. So finally, we can solve for our total cross-section. So let's look at the total cross-section. My arrow keeps breaking, so let's switch to something else. So now we have the total cross-section. Sigma is then equal to the integral of d sigma, which again is equal to the integral of that differential cross-section integrated over the solid angle. So good. So now using this guy, this is then going to be equal to the integral of then z prime e squared over 4e quantity squared sine of theta d theta, and I'm going to get a factor of 2 pi out front from that d phi portion, all divided by sine to the 4th of theta over 2. Now, here, we're going to go ahead and integrate this. We're going to integrate this guy now from 0 to pi. And one thing to note is that what? So basically, if I integrate here, I'm going to get a basically sine over cubed, basically. So this is going to be proportional like a 1 over sine cubed. And as it goes to pi, that's going to go to 0, and this is also going to go to 0, which means I have a 1 over 0 cubed, which is going to basically mean that this thing is going to go up to infinity. I'm not going to do the entire integral, but let's just argue it that way. So basically what that means then is that this total cross-section is infinite. So as this thing integrate over, that thing is infinite. Now to understand what that actually means, let's do a slightly easier problem to try to figure out what does this cross-section mean before we interpret what this infinite cross-section means for the Rutherford scattering. So this simplified example we're going to look at is then what we call hard sphere scattering. So hard sphere scattering basically means that we're going to, again, take some particles, we're going to shoot them in, or we're going to shoot them into a sphere which has a radius of capital R, meaning that basically we're looking at a potential which is well defined in some small region. Okay. So basically I'm going to go ahead and shoot some particles here. So this is going to be my mass m moving in this direction with some initial velocity v. These particles are going to come in, hit, and then once they hit, they're going to then scatter off in some direction. Right? These are going to go flying off in this direction. So these are going to come in initially here and then scatter off in this direction. Now, the type of scattering this is going to have will be then what? Elastic collision. Which means that these particles are going to come in, they're going to bounce off at exactly the same angle at which they come in at. Okay? Which basically means if they come in at an angle of alpha, they also come out at an angle of alpha. If I extend this line over here, this is then also equal to alpha. Now, the nice thing about the hard sphere scattering is we can do completely geometry to figure out how B actually depends on the angle of theta. So this is my scattering angle of theta. So the first thing note is that this whole entire has to be pi, and that's going to be equal to twice of alpha plus then theta. The other thing to note is that we can redefine this impact parameter b as then being this distance here, and since this is the radius of r, this is my line that connects the two of those, that means then that b is the same thing as r times sine of alpha. So b then is just going to be r sine of alpha. Now one thing to note here is since this has a potential which is well defined within inside of this radius, if my impact parameter is bigger than the radius of this object, automatically it tells me I'm not going to hit it. All my particles are just going to go by it and completely miss it and never interact with that potential as it is. So good. So from here, this then gives that alpha then is going to be equal to what? Pi minus theta, all divided by 2. So it's going to be the same thing then as what? R times sine of pi minus theta divided by 2. But sine shifted by pi over 2 is actually the same thing as cosine, so this is the same thing as r cosine of theta divided by 2. Right. So, now that I know that, I can now determine the differential cross-section, which again is d sigma divided by d omega, which is going to be b divided by sine of theta dB d theta. So take a derivative of that. This thing is going to be equal to then, I'm going to get an r squared, get an r from the b itself, and I get an r from the derivative, divided by 2 sine of theta times sine of theta divided by 2, so that comes from the derivative, times cosine of theta divided by 2. So good. So notice 2 sine of theta is the same thing as what? Do it this way. Sorry. Cosine of theta times sine of theta is the same thing with a 2 as sine of 2 theta. So that's going to be actually the same thing as what? Sine of 2 theta. So this is actually the same thing then as r squared divided by 4. So here I'm just using then sine of theta times cosine of theta is equal to 1/2 sine of 2 theta. So here, this is theta over 2, so this is just going to become theta. So I get an extra factor of 2 down, which is where the 4 comes from. And then these two things are simply going to be the same thing as sine of theta. So these terms cancel with this with an extra factor of 1/2. Right. So this means then that the total cross-section is going to be equal to the integral of the differential cross-section integrated over the solid angle. So integrate this guy. This is going to be the same thing then as what? I get a 2 pi from the d phi, and then I get a sine. So this is going to actually be the same thing as pi times r squared. So this is my total cross-sectional area. So what does this mean? This is kind of the big question. So what this means then is what? Let's use this to interpret what the total cross-section is. So the total cross-section then is, if this thing was a sphere, then what this thing is looking at then is the effective cross-sectional area of the sphere, which means it's looking at this area here. So sigma then is equal to the cross-sectional area, which we know is the same thing as simply pi r squared. So what this means then is, even though I have a sphere which is sitting here, if I'm sending particles on it to then scatter off of it, what it sees then is simply that cross-sectional area of this object at which I'm shooting at. This is what the total cross-section means. So the total cross-section then is the effective area at which my particles see, my incoming particles, at which they can scatter off of. Now, if we go back to the Rutherford scattering, so again, what we found was in Rutherford scattering, this total cross-section then was effectively infinite. So what does that mean? So that means that the incoming particles at which are being shot at it, what that sees then is an infinite cross-section, which means that it sees an infinite effective area. So what does that mean? So that means that the potential in this case extends all the way out to infinity, which means that what it's seeing then is it's interacting with this potential anywhere from the center of potential all the way out to infinity. Now, again, the closer that it is to the center of potential, the more of an effect that you're going to see. But again, even if I had a particle which was way out here, which is moving in towards the center potential, again, in the Coulomb scattering, there's going to be some small, slight deviation due to the fact that it's still interacting then with that potential. So what the total cross-section then is again, it's looking at that effective cross-section that it's seeing. Again, meaning as I'm shooting in these particles, where is this thing going to interact with the potential? Now again, if I have a well-defined potential like this sphere, what it's seeing then is only that effective cross-section, i.e. the cross-section of the actual object. But if I'm looking at something like the Coulomb potential, which extends all the way out to infinity, well then it's seeing all of that infinite extent at which this potential is actually going to interact. Again, more interaction happens the closer you get to the center of that potential, but there's still non-zero interaction even if this thing is on its way out to infinity. So the total cross-section then happens to be with the fact that it's talking about what extent is this potential interacting with the incoming particles at which are coming in. So, again, going back to Rutherford, it makes sense then that the total cross-section is infinite because the extent of that Coulomb potential is also infinite. This would be the same thing with gravity. So if I had a 1 over r squared force, meaning I have a 1 over r type potential, even with gravity, that central potential extends all the way out to infinity, which means that the total cross-section in that case would also be infinite, whether it is for an attractive or repulsive type potential. These two things would be the same. So again, it makes sense because as I'm shooting at that target, the extent of the potential is infinite, therefore the area at which I'm interacting with is also infinite. So that's the end of this chapter. So next videos then we'll deal with chapter 7, and chapter 7 is going to be harmonic oscillation. So we'll start those soon.